So first of all, I really want to thank the organizers for organizing this. Yeah, it's really nice to be here to again talk about stuff. It's a pity that it happened after the SIDH break, so I have less things to talk about, but yeah, life goes on. So thank you for coming, and thank you for having me again. So this really should have a subtitle, which is what to do with your life when SIDH breaks. And I first accepted this talk when it wasn't broken. I was thinking to myself, I need to exclude this, I need to exclude that, so that I can fit it into a talk. After the break, I was thinking, what do I do to pad it up? And you'll see all the little things that I've done to try to make this longer and more acceptable. Okay, so if I end early, have a longer coffee break, and thank Walter and Chloe and Luciano for that. Yeah. So I'm just going to give an overview of what I'm going to cover. So I understand that a lot of times when I was a young PhD student, coming to these events, you're being thrown to the deep end and you don't quite understand what you're looking at. So I would like to pitch this towards a more younger audience and just explain to you what hyperelliptic curves are, if I can, isogeny graphs, and before that and after that, I'm going to move on into cryptography. I'm going to explain things about hash functions, cryptanalysis of hash functions, the state of genus 2 isogeny cryptography. I also talk about the FASTA encryption scheme that Luciano talked about just in the morning. And then after that, I'll try to again maybe tell you what I'm planning to do next, how to piece my life back together. Yeah. Okay. Yeah, let's get started. So I'm going to start with some arithmetic and geometry. So we all seen elliptic curves. This is nice and simple. This is basically a curve given in P2. And this is what you see in the rails, right? And we also know from undergraduate mathematics, you can take 2 points. You draw a line through them, you get R, and then you can reflect that around and you get some additional points. So this is nice and easy. So we can also do this for hyperelliptic curves. Hyperelliptic curves are just given. It's just a generalization of elliptic curves where instead of thinking about y squared equals to a cubic, you think of y squared equals to a sextic or quintic. And so in this picture, I have 1, 2, 3, 4, 5. So this is actually y squared equals to x times x minus 1, x minus 2, x minus 3, x minus 4. And this is what it looks like in the real line. So you can play the same game, but it's not quite the same anymore. You can't just take 1 point and draw lines through them. You need to take pairs of points. So in this diagram, you have P1, P2. This is going to be one group element, if you like. So this corresponds to the P that you saw before. And Q, you need to split it up into 2 again. You need Q1 and Q2. And now what you can do, you can draw a cubic that fits through all 4 points. And you get this nice line. It cuts the hyperelliptic curve in 2 other points, R1, R2. And you flip it around, you get this. So this is a nice geometric representation of this, which I found really helpful to understand how you go from genus 1 to genus 2. Okay? So it's not at all obvious when you go to genus 1 to genus 2 that the geometric points are actually the ones that are doing the group operation. Because right now, you don't see actually the geometric points doing the group operations. You need 2 of them. So it's not that each point on the curve is a group element. And this is the reason why we have this group element, if you want to go deeper into it, is you look at Jacobians and you really look at the devices for this. So this, you let E be an elliptic curve. Then the Weil devices is just a formal sum of points. So this is for a curve, yeah? For if you want to go into higher dimension, if you want to go into more complicated varieties, then it's no longer points. But for now, if we're looking at curves, these will be points. So the Weil devices form a group under addition, and this has to be a finite sum. Okay? So the degree is given by the sum of all the coefficients. A principal divisor is something, I still admittedly have trouble getting my head around. Basically, these are just rational functions, if you like. Rational functions you try to associate the divisor to the rational functions. And basically what this divisor does, it counts the zeros and the poles of this rational divisor. So it's some sort of good bookkeeping, if you like. It counts how many times the rational functions interacts with the variety you're interested in. Yeah. So this is all good and well. And now you're in a position to try to describe the Jacobian, which is the divisors of degree 0 modulo the principal divisors. And this one gives you the Picard group. And then the theorem is the one that actually gives you the group action, right? Or rather the group structure. So you have this map where you have this divisor mapping into a point on the elliptic curve. So the same thing happens. This is now puts you in a very easy position to abstract everything and go into genus 2, for example, or higher genera. So Jacobians of hyperelliptic curves are abelian varieties, and we're actually interested in genus 2 hyperelliptic curves. And these are the ones whose Jacobians are actually abelian surfaces. So again, this is a concept that I had to understand before I could work on it. Okay? And also abelian surfaces, besides just looking at the Jacobians, you can also they also include products of elliptic curves. So there are two kinds of so it splits into two different things: the reducible ones, which are products of elliptic curves, and the irreducible ones, which are Jacobians. And then there's a special property that arises when you take Jacobians, which is you bring along this thing called principal polarization, which you want to keep and you want to keep track of for the rest of this talk. There are other structures that you can consider on abelian surfaces, but this is for later on. Okay, so you want to keep this principal polarization, you want to keep track of this. So as I said, I was just jumping the gun over there. There are other properties that one can choose to keep, for example, CM, RM, and also other more fun stuff that you can choose to take along with you on the ride. But for now, we'll just keep the principal polarizations. So I'm just going to talk about isogenies and isogeny graph. This is not supposed to be there, it's just overlay. I just forgot to index them properly, sorry. So anyway, morphism is an isogeny. It has finite kernel and it's surjective. So this is what you see. You've seen this a couple of times throughout today. So you might be tired of them, but this works for abelian varieties in general. So there are two fun facts. Basically, one that isogenies are group homomorphisms, and that if your isogeny is separable, then the degree is equal to the kernel. So this is nice and established ground for us. Now, there's a one-to-one correspondence between finite groups and separable isogenies. So in cryptography, you do not want to study, you would like to study isogenies, but sometimes isogenies are too cumbersome to take around. And so you want to find a nice representation, and this is one of those nice representations that allow you to describe an isogeny fully. So instead of looking at polynomial maps, you can just look at finite subgroups. And most of the time, these finite subgroups are finitely generated. And so then you can look at kernels which have much more compact representations. This is why this is important. Okay, so this all lends itself very well to cryptography so far. So, but recall that we actually want to keep track of principal polarizations. So you will see over here that there's a one-to-one correspondence between finite subgroups and separable isogenies, but it makes no mention for what happens to polarizations. And if you want to consider polarizations, you need to take into consideration isotropy, which is just some very pairing computation that you need to do. So it's very nice and easy to do. This isotropic condition is actually on the subgroups, and you just need to consider them. Okay. So we want to consider L isogeny graphs, which have vertices abelian varieties. The edges will be separable L isogenies, but as you recall, I want to look at surfaces. So we focus on isogeny graphs on principally polarized abelian surfaces, and so we change the vertices to isomorphism classes of principally polarized abelian surface, PPAS, and the edges will be LL isogenies. These just happen to be the ones that preserve principal polarization. Okay? So this is just a picture for the two isogeny graph. I've seen many ways of displaying isogeny graphs, and they don't give you information, so I decided to put them in a circle anyway, because they don't give you any information anyway. So just for variety. Okay. Yeah. So now I'm going to move on to cryptography. A hash function is a function that takes a bit string of arbitrary length and maps into a big string of a fixed length. So what you want to do, you want to ensure at least two properties hold. You can have more, but what we want to do is we want to consider at least these two, which is collision resistance. This means that you want it to be as injective as possible, because clearly, if you have arbitrary length strings mapping into something which is smaller, there's no way you can achieve injectivity. But in a hash function, you're never going to be able to, I mean, that you just don't have enough computational power to cram so many inputs and try to find the you want to make it such that it's so difficult to find the injectivity, even though you know it exists. So this is more computational difficulty. And the second property that you want is for pre-image resistance. This means that it's hard to invert this hash function. So given an output, it should be hard, computationally hard, to find the thing that maps into it. So this is just going to be a preview of the hash functions on isogeny graphs. So I showed you an isogeny graph just now, and I showed you a hash function. So the most logical thing is to put the two of them together. The input would be some string of bits. The output will be a vertex on the graph. And the method that you're going to use to obtain this output from the string is to conduct some random walk on the graph using the input. And so that when the output of the graph, the final vertex of the walk will be the output of this hash function. Okay, so you need to again check that you have collision resistance and pre-image resistance. Okay, but yeah. So a hash function in genus 2, I'll just like to go through the history for this. So in 2009, Charles, Gorey, and Lauter, they showed that brand matrices are Ramanujan. And they just hinted that you can actually look at supersingular abelian varieties to create a hash function. So Ramanujan just means that it's an expander graph. So you only need to walk a couple of steps, when I say a couple, sufficiently many steps before this becomes randomly distributed. But they didn't actually prove it prove that it's Ramanujan for the supersingular abelian varieties because this is not true in general. It's not Ramanujan in general, okay? But this is the first instance of genus 2 that I've seen in cryptography. Then in a different paper, but in the same year, the three of them proposed using the supersingular elliptic curves, isogeny graphs, to realize a hash function for genus 1. And then Takashima outlined a hash function using 2-2 isogenies in the super special graph of abelian surfaces. So this is in 2018. So I'll just show you how this is done. So first of all, you set a prime P and a vertex. So this will be just some random vertex in the graph. You use the input bits to choose a non-backtracking path at each vertex. So that means you need to know it's a stateful hash. You need to remember what vertex you were on before, and make sure you do not go back. Otherwise, it's very easy to find collisions, right? You just keep going in cycles. You output the final vertex, and this is it. So this is a hash function. It's super simple. So Jordan and Zeidman actually showed that this graph is connected and actually has expanded properties in 2020. I think they presented it at ANS or something. And so the security properties of collision resistance and pre-image resistance still hold, right? You want this to hold true for a hash function. So we're going to look at collision resistance in particular. So to understand all these graphs and all these hash functions, you need to understand the isogeny graph better. And the isogeny graphs are huge, so you need to be able to get a handle on them. And as I showed before, sometimes you just need to find a good representation of it. And a good representation of this is actually via looking at the kernels. So isogenies can be studied not by looking at them as a big graph or as rational polynomials, but if you understand how the kernel behaves, you get to understand local properties of the graph. Okay? So the first result that Victor Flynn and I realized was that, well, if you want to study the groups, first of all, you need to understand how this behaves in a subgroup. So if we are looking at, for example, in Takeshima's hash function, we are looking at 2 isogenies. And so L is equal to 2. You're looking at 2 power torsion elements in the on the Jacobian. And so you need to understand subgroups of this bigger group, of this torsion group. And we found that, well, the maximal isotropic subgroups, basically these are the subgroups that give us paths in the graph. They look like they have rank 2, rank 3, or have rank 4. But rank 4 correspond to just scalar multiplication. So these are endomorphisms, and they give you very simple paths in the graphs. So this is actually a backtracking graph. So we don't actually, a backtracking path. So we don't actually want to consider them. We want to focus on the rank 2 case and the rank 3 cases. And so the proof of this is actually fairly simple. So first of all, you rule out the rank 1 case where k is cyclic. So if this is cyclic, then actually it's embed, so it's not maximal. And then for rank 2, you just use the maximality of the subgroups is quite easy to show, how you cannot embed further. And then for the rank 3, you just need to use the symmetry of the kernel of the dual isogeny. And this just forces the structure to come out this way. Okay, next. So the question is, now that we understand the subgroup, how does this affect isogenies? Well, this is the number of elements. So you kind of you want to understand how the path determines the number of elements it will touch in the isogeny graph. And this just gives you a way to measure them. So if you look at n sphere where n is not large enough, so n cannot be too large such that it overwhelms the size of the isogeny graph. But if this is true, then you can count the number of balls that you, the number of, how do you say this? Abelian surfaces that you reach with this hash function, depending on how many steps you have taken. Okay, again, this is just counting the number of L maximal isotropic subgroups, and you sum them together. You get this result. It's fairly simple. But now I want to understand, so remember I talked about the collision resistance of hash functions. This means that I should not have 2 different paths that meet up again at the output. Okay? So having this sort of going in 2 different directions but meeting at the same place, this is bad. This is not what you want in a hash function. So first of all, you fix some prime L, some prime P. L is going to be 2 again, and you fix some abelian variety, principally polarized abelian surface. You consider some kernel. So you want to fix Ln maximal isotropic subgroup. You want to ask how many ways can you go from A to AK. So this is the codomain. So the key observation is that you need to understand how many times or how many different ways CL cross CL can go into K. So this really depends on the subgroup structure of K, right? Or rather the group structure of K. So I'll give you a simple example. So first of all, you pick some P, you pick some A, you fix them. So you let L be equal to 2, you consider this kernel structure where this is a rank 3 kernel. So it looks like C4 cross C2 cross C2. So because K has order 16, you expect this sequence to break into, factorize into 2 isogenies, a two isogenies. Okay, a dual, well, I don't know, a pair of two isogenies. Yeah, too many twos in there. So you need to understand, well, how can I pick the first isogeny? Well, how many times does C2 cross C2 go into this K? And you don't just want to count the number of C2 cross C2s that go into K, you want to count C2 cross C2s that are also maximally isotropic. So the thing that we found is that, well, the first step, you actually have 3 different choices. So if you take this to be generated by P, generated by Q, generated by R, in the first step, you can pick twice of P, so this is going to be a 2-order point. You pick Q, which is an order 2 point, and this is going to be maximally isotropic. One can check this. But alternatively, you could pick twice of P, you could pick R, or you could pick twice of P, and then Q plus R. And this gives you 3 different paths. And for the next step, well, you don't have any choices anymore. The moment you quotient K by one of these, you just get C2 cross C2 and you don't have any choices. And this just mapped down to X again. So you can take this structure, you can actually try to look at different kernel structures. So for example, if you look at C16 cross C8 cross C2, you can see this diamond thing coming out again, and also over here, and also over here. So at each point, all you have to do is to understand how many times you can have C2 cross C2 existing as a maximally isotropic group in your remaining subgroup. So over here, once you come here, actually you see that it's a straight line all the way down, because at this point, once you map this kernel through, what you get is C4 cross C4. So you don't get any choice, you don't get any choice. But if you go this way, you still have some choices. If you don't kill off the C too early. Yeah. Again, we have C16 cross C4. You get C diamonds everywhere. Yeah. And in the 2-sphere graph, for example, you have diamonds actually over here. It's just they're there, but you don't see them very well. But I think this is very instructive, because if you go back to thinking about hash functions again, this, for example, is your starting vertex. If this is your final vertex, then what happens is that you have different paths. You have different input bits that take different paths and meet at the same output vertex. And so this means that what you have is a collision. You have found a collision in your hash function. So we can actually count the number of paths if we want. And the number of paths is actually given by this recursive formula, because all you have to do is just to pay attention to which path you were on before, and you just count them up. And actually it's just bookkeeping, it's just tedious bookkeeping, and all these formulas just fall out. So there's a closed form, but it's not very nice, so that's why I don't display it. So the upshot for this, for the hash function, is that it's easy to find collisions if your path contains diamonds. So what Castrick, DeCreux, and Smith, they proposed, they saw this paper, they decided, you know what, actually we can do better. If you understand the Wish-Low isogenies, you're able to find a way such that the extension, so if you have a Wish-Low isogenies, you have a Wish-Low isogeny, if you want to extend the Wish-Low isogeny, you can actually understand how to avoid those diamonds if you do some bookkeeping and understand how exactly you want to extend it. So what they did was that they have paths that do not backtrack and avoid collisions. And this compared to dimension 1, because Charles Goy and Lauter has done this in dimension 1, we can see that in the supersingular elliptic curve case, what you normally have, you have 3 isogenies, right? But because you do not want to backtrack, you only have 2 isogenies, 2 non-backtracking 2 isogenies. So the question is, well, you have one for genus 1, why do you want another one for genus 2? And the answer is because in a principally polarized supersingular abelian surfaces, you have 15 2-2 isogenies, and you actually have 8 of them that are non-backtracking, and they have good extension. So good means you avoid collisions or the diamonds. So, so each step, you're able to process 3 bits of information instead of 1. So you can, hopefully it's more efficient, but it's up to whether value formulas perform better on elliptic curves or wish law formulas perform better. So there's a trade-off that needs to be found. But so far, no one's using elliptic, hash functions on elliptic isogeny graphs anyway, so it's a moot point, really. So what happens when you hit the product? Because actually, I didn't tell you this because it's going to come later on, but there are products, I told you this actually before, but there are products within the isogeny graph, right? But what happens when you hit a product, when you end at a product, or when you encounter a product en route during a computation? Would this break the hash function? Well, so this actually produces a vulnerability for genus 2 isogenies. Isogeny cryptography, yes. So super special graphs for dimension 2 and above, they contain reducible abelian varieties, which I mentioned before. So the probability of these abelian varieties occurring is actually 1 over p. So it's actually quite small, but it's still there. But what you're able to do is that you can treat these as exceptional points. So what Costello and Smith did in 2020 was to come up with an algorithm that searches for these reducible points in the graph. So these reducible vertices become special points that they try to find, and they're able to keep iteratively find reducible varieties, such that you're able to obtain a classical algorithm that performs much better than a PG square root. So this is much more efficient than the usual way of actually just running through the graph. Okay. So the aim of the attacker, as I said, is to find reducible vertices, and this is actually like akin to finding, it's like a special way, finding special vertices in the graph. And so the example of something like this actually happened for elliptic curves. We are actually finding distinguished points on the supersingular elliptic curve graph, and these distinguished points are actually points that are defined over fp instead of over fp squared. So this is like a generalization. This algorithm is a generalization of a result by Christina Dels and Stephen Galbraith. So it seems like genus 2 is a sweet spot, because if you go up into higher genera, you'll notice that actually this algorithm becomes a lot more efficient than other algorithms, than the naive algorithm. So genus 2 is the sweet spot, but you still haven't removed the products, so it's still there. So can you remove products, perhaps? So this is where I'm going to start to talk to you about super special and super singular. I know I've been talking about them quite a bit, but not without defining it. So this is why I do it. So in the elliptic curve case, I like to motivate things from elliptic curve because I hope this is more approachable. So in the elliptic curve case, we begin with some elliptic curve over a field of characteristic n. And you want to look at what happens to the p torsion. So in the elliptic curve case, we all know that the p torsion vanishes. And this should be a set, or group, sorry. And actually, we also know that endomorphism algebra is a quaternion algebra, is an order in the quaternion algebra. No, the endomorphism ring is an order in the quaternion algebra, sorry. So, when you go to higher dimensions, we say that A is supersingular if A is isogenous over the closure of a field to a product of supersingular elliptic curves, and A is super special if it is isomorphic over the closure to a product. And we actually have something even stronger, right? We don't actually need to be a product. We actually have a power of a particular elliptic curve. So any elliptic curve you choose. So if you have A, an abelian variety over char P, then if you have, then you actually have A is isomorphic to EG. But this happens as abelian varieties. So you in this particular slide, you don't actually want to keep track of the principal polarizations. These actually happen without principal polarizations coming into play. So this looks very special, right? This looks amazing, but that's because you are omitting certain things. So more about super special and super singularity. What happens when you see that the p torsion disappears? It actually doesn't actually disappear, right? It's a bit like energy. Energy does not get created or destroyed. It just becomes something different, maybe something you cannot see. And this is the same for the p torsion. So if you look at finite group schemes, then they come back alive. You start to see them appearing. So you define the additive group scheme and the multiplicative group scheme, and you can start to see, start to try to understand how the p torsion contains, or rather is mapped into by the multiplicative group scheme, and this is given by the p rank. The A number counts the number of ways that you can map the additive group scheme into the p rank. And it holds that all these inequalities are true, but I think more importantly is that geometrically, you actually have the p torsion being described by the p rank, which is what you expect to see. Okay, but I think to specialize in the super singular abelian varieties, or rather abelian varieties, what we have is this following table. So these are all the numbers that are possible, and you have the p rank and the A number, and this gives rise to different types. So you have ordinary, non-ordinary, super singular, and super special. So in elliptic curve, you only get two different categories. You have ordinary and you have super singular. In dimension 2, you have more. You have all these things coming out, and then the p torsion is described using, they're still there. L actually describes what the geometric points are, but as you see, when you look at the p rank disappearing, actually you don't have the geometric points anymore, but these are described using some group scheme that I want to go into. Okay, and you can also see, I think it's interesting to understand what the codimension is. So the codimension describes how large the ordinary abelian surfaces are. So the dimension, the dimension of the moduli space of abelian surfaces is 3. So the codimension of this is 3, which means it's large, right? Non-ordinary is slightly smaller. Super singular, interestingly, is actually codimension 2. So that means it's dimension 1. So there's infinitely many of them. Okay, but the super special ones, there's only finitely many of them. And so far, we've been working on the super special isogeny graph. But what we are proposing, actually, is that what we can do, we can move from the super singular to the super singular non-super special graph. So this is the third one over here. All the genus 2 isogeny-based cryptography so far has been happening on the super special graph, because this is where everything is nice and easy. You can glue graphs together, and you can get a random abelian surface. Well, random. You can get some abelian surface, and then you can start doing all your genus 2 isogeny-based cryptography. But for super singular, non-super special, you're not able to do this. And this is why maybe people haven't started looking at that. But we are advocating for a move to super singular, non-super special. And the reason for this is that if you work over L, where L and P are co-prime, you do not actually get reducible surfaces anymore. You need to, the only way you can get reducible surfaces, because they are still isogynous. It's just that the only way you go from the super singular into the super special component is via P isogenies. And these P isogenies will be factors of the Frobenius or factors of the Verschiebung. And these are, I have no idea how to compute them. So if you have any ideas how to compute them, please come and let me know. Yeah? Because it'll be interesting. And also, because there are infinitely many of them, you actually have to work over extensions of finite fields. So you work over extensions of fp squared, and this might not be so good for cryptography, but you do avoid products. So what we actually say is that, well, we analyze the hash function of Castrick, DeCoux, and Smith, and they have three strategies for when they end on reducible surfaces. The first one is to ignore them. The second one is to deterministically find a non-reducible neighbor. And the third one is called gluing, but number 2 sounds like number 3 to me. So yeah, not too sure. But anyway, they chose to ignore them. And this raises the possibilities of hash failures. But if you move to the supersingular non-superspecial, everything stays the same, but you are able to remove the possibility of failure. So not too sure what the downsides are, right? It seems quite simple. But all you have to do is to find the starting vertex, but actually that's not a difficult problem as well. There are well-known ways to find supersingular non-superspecial curves using results of, for example, Ibukiyama and Ott and Katsura. So what happens when you encounter irreducible surfaces en route? Actually, what they do is that they have a if statement in their code that helps you glue them back again. But this shows up very easily on side channel analysis. And once you see that a reducible surface has appeared, you can try to do some mid-in-the-middle attack, and this really reduces the security level. So you can look at this paper for more information. So this is the latest paper you've seen. The other paper goes all the way back to 2019, the pre-COVID times, where, oh yeah, by the way, this is, I've forgotten, this is another slide. So this is the supersingular non-superspecial graph, right? This is, again, this is the classic way you see this, but yeah, it looks messy enough. So maybe it's good enough. But more cryptanalysis needs to be done, of course. But yeah, I talked to you about a lot of Genus 2 stuff so far, but it's either from 2019 or 2022. So what happened in between all those times? Well, actually we have a lot of results that talk about Genus 2 isogeny cryptography. For example, we have a generalization of SIDH. We have attacks on SIDH, and also there's this failing to hash into isomorphism classes of SS supersingular elliptic curves. Because this is a failed attempt, I won't talk about this in this talk. And there's also another result called breaking SIDH using Genus 2. So I won't talk about these two things anymore. So that leaves me with very little things to say, right? So I need to look at what other people are doing. So there's also the ski sign HD. This is trying to embed isogenies of supersingular elliptic curves into higher dimension so that you're able to represent them more compactly. But another crypto system that came out using Genus 2 is this Festa that Luciano talked about this morning, and he uses Carney's lemma constructively. And because I have nothing else to talk about now that everything is cancelled, I will focus on talk about Festa. And this is actually joint work with Sabrina, Luciano, and Lucas. So Sabrina and Luciano are here, but unfortunately Lucas can join us today. And also I want to thank Giacomo for helping with the code. But what we saw, Festa, uses a trapdoor function for encryption. The decryption function actually looks like this. You put in your secret key, you take your ciphertext, you either output the message or you output a failed statement, okay? The ciphertext can be chosen by the attacker because the attacker provides this ciphertext to some decryption oracle, right? So I can choose any ciphertext I want. It doesn't have to be the correct ciphertext. I can choose it and change it according to what I want. In particular, the ciphertext contains 2 elliptic curves and 4 points. And this R1, S1 belong in E1, R2, S2 belong in E2. So if I'm able to change this, will I be able to obtain some parts of the secret? That is what I'm trying to do over here. So just for completeness, the secret key is given by this K1, K2, which are secret isogeny subgroups, and this B is actually A. Yeah, I should have called this A. So this A is a secret 2 by 2 matrix. Yeah, this is. So in Luciano's talk, this was A. I forgot to change this, I'm sorry. So the output of this decryption function, as I said, is either the message or some failed property. So it outputs 1 bit. Okay? So the oracle model that I'll use is, well, I'm going to put this ciphertext. This ciphertext is going to be of my choosing. I'm going to guess M. Okay? So my guess of M, hopefully, will give me some information about the secret, which is what is put into the decryption oracle. So the oracle will return a failed statement if this doesn't, my guess is wrong, and it will return 1 if my guess is correct. So what I do over here is, first of all, the attacker has a pair M and C. So let's just say he magically cooked this up, okay? But if you have an encryption scheme, since this is a PKE, a public key encryption, you should be able to obtain this plain text ciphertext pairing. So it's not impossible to think that this is this can happen. So again, you recall that the ciphertext is this. The oracle, what it does to compute this H, this secret subgroup, it will take this alpha and beta, which are secret. These are, yeah, maybe the board will be helpful now. So you have A, which is also equal to B, which is equal to alpha, beta, 0, 0. This is the matrix that Luciano presented earlier this morning. So what I want to do is I want to recover alpha or beta, ideally both. Okay. So, but this is how the R1, R2, R1, R2, S1, S2 are used in combination with the secret key. So, again, a common thing of this is you need to understand how the subgroup structure works. And actually, if you want to understand how the subgroup structure works, all you need to do is to understand what kind of elements appear in the subgroup. And what we actually have is you have this, you have R1. You can add elements across to get this, or you can scale them to get this. So these are two different ways that you can obtain new elements. So the oracle model is this. The attacker chooses a set of points where R1, R2, S1, S2, this should give you the original, should correspond to the original plain text. But now you're choosing something slightly different, right? You're choosing R1 prime, R2 prime, S1 prime, S2 prime. And these look different now. And the reason why we choose this is that the oracle will be computing this. It plugs this into this subgroup. So this point is R1 prime. This point is S1 prime. This is R2 prime, S2 prime. It doesn't know that, it's not able to see that it is malformed. It wouldn't know to the oracle or to anyone who's sane, this just looks like a string of bits, right? So you won't be able to tell that there's anything different. But what the computation does is that when you multiply this out, alpha becomes alpha naught and then alpha 1. So this is the 0th bit of alpha. This is the first bit of alpha. So this tells you whether it's odd or even. This tells you what is it, what for example. So because we know that alpha and beta are actually odd, we know that alpha naught is 1 and beta naught is 1. Whereas this alpha 1 is something you need to recover, and beta 1 is something you need to recover as well. So if you just bash through the algebra, this is what you have. You have two different cases appearing. This one, the top one and the bottom one are the same, and the two in the middle are different. And this is great, right? Because if you recall, if you look at this, this is R1 plus S1, alpha R2, beta S2. And this is exactly the same generator as what we had before. And you can check that this actually also appears as the same generator. And so what this means is that this is the same as the secret generator from before. So if we were to feed this points, and alpha 1, beta 1 is equal to 0, or alpha 1, beta 1 equals to 1 and 1, then this too will give us the correct guess on the oracle. Whereas, if you look at the other two cases, this kernel is different from this kernel. And so therefore, this will return a failure. And so by understanding whether you pass or you fail the oracle, you're able to guess whether the bits are the same or different. So this is one bit of information. But the problem is, the decryption is actually protected by some OAEP protocol, which is some padding protocol. And this is able to turn this trapdoor function into a CCA secure scheme. But we are able to recover one bit despite that. So I think it's pretty impressive. But while the recovery of the next bit is underway, we found that actually the OAEP is actually very good, and so far we are not able to get past that. But we should be able to attack the trapdoor because the trapdoor doesn't have an OAEP. And it should be noted that the trapdoor model does not consider the adaptive attack. So we are hopeful that this can be done. But I've been burned many times. Hope kills you, really. So attacking a variant of FASTA, we are actually attacking a variant of FASTA where these are diagonal matrices, whereas in Luciano's talk, you also saw that you can actually have circular matrices. So this is alpha, beta, beta, alpha, yeah. So you can also, the question is whether you can extend what we hope to do to more variants. So attacking a trapdoor, so you can also attack the trapdoor and extend it to attacking the encryption protocol by adding in side channel information. So this just means that, well, we want to know what causes the decryption failure and what can we learn from that. So this is like adding more information to the attack. So what is next? Well, I don't have time. I have 5 more minutes, yeah? Yeah, okay. So I won't show you the demonstration of the attack, but if you like to, you can come down and take a look later on. But what I like to do next is I like to generalize C-side to genus 2, for example, and because it sounds fun. So, but what we need is we need better implementations of isogenies on abelian surfaces. This would involve speeding up Robert's implementation of AV isogenies. We need to understand endomorphism rings of abelian surfaces better. And we also need to understand genus 2 graphs better. And this is why, if you've been bugged by me, this is why I've been talking to you so much. And also, I like to generalize key sign. This is even more difficult. You need to generalize KLPT. You need to be able to compute the Dorian correspondence in genus 2. And I'm pretty sure that these crypto systems won't be efficient, but I can guarantee that they'll be very fun to do. And in particular, for C-side especially, because C-side you have 2 directions. And each direction gives you, it's 1 bit of security, for example. If you generalize this to genus 2, you still have 2 directions, but each computation is going to be more expensive because you're working genus 2 instead of genus 1. So you have to do the same number of computations, but each computation is more expensive. So what's the point of doing that? Fun. Yeah. So this is the last slide. I talked to you about elliptic curves and Jacobians, isotropic groups. I talked about cryptography, so hash functions, constructive and destructive applications to cryptography in my life, and also I talked to you about FASTA and how you can recover 1 bit. So I think this is a good time to end, and I'm happy to take questions. Oh yeah, by the way, I tried to fit everything, but there's no codes, I'm sorry. So thank you, and if you have any questions, I'm happy to take them.
Okay, are there any questions for Bo? Yes.
Thank you, Bo. Could you say a little bit more about how you find a super singular, non-super special Jacobian?
Yes, I can actually. So, I don't remember the exact conditions, but if you consider this, for P congruent to something mod something, I think this is 8, right? Maybe Tomoyoshi, maybe you can help me here. But P0. Yeah. P now right now P is because 0 because of the question mark. Maybe it's question mark prime. Yes. But there are conditions when this is going to be super singular and non-super special. Actually, there are more constructive ways that you can do this as well, but I think this is the easiest to explain in 1 minute.
Thank you. So you can find this one and you can find isogenies from that, I guess.
Yes, exactly. Then you just take visual isogenies and you can go anywhere you like.
Thank you.
Are there any more questions? Yes, Jean.
Thanks. So you talked about these super singular, non-super special graphs.
Yes.
So I'm assuming if you restrict to like some field of definition, you still get something finite.
Yes. If you restrict the field of definition, it will be finite. Yes.
Right. And is anything known about like the structure of this graph? Are they connected? Are they standards?
If you are very restrictive with your field of definition, they're actually not connected. So you actually see components here and there. So yeah, but the big component still seems to, so the number of vertices actually grow according to the field of definition, the size of the field. But the individual components, that's a very good question. But this is, we've ran a couple of stuff. So the image you saw just now with the messy graph, actually that's just one component. Yeah. And does this lie on the big component? Yeah. So maybe this is why our paper got rejected, which is fair. Yeah. So this is in anticipation for people who want to see whether the attack works. Yeah. But if you don't, it's fine. We can go for T.
Okay, Niels?
So how does that attack work?
So the attack works by, so we have this alpha, this A, which is this number over here, is given by this big number, which is alpha, and this is beta. Oh, well, whether this is beta, this 2, 6, blah, blah, blah. And so if you run this, you see that because this is going to be, you'll see that this is 1, 1 mod 4, this will pass without any problems. So that means we get a decryption and everything works fine. But if you were to change this, change the secret, oh dear. Then you see that an error occurs in the decryption. Yeah, so the error message is not very well written, but you can use this as an oracle. Whether you get an error or not, you can learn 1 bit. So far we can only do 1 bit. Yeah.
I have a general weak question. So in classical hyperelliptic curve discrete log problem, there is a clear way to compare, say, genus 1, genus 2, and higher genera where people know that there is no sense to continue because there are attacks in the case of genus greater than 2. Yes. So what's the situation in the isogeny-based cryptography? First of all, can you compare genus 1 and 2? and say if there's any sense in attempts to making genus larger?
Yeah, I think that's a great question. So we come back to this result by Castello and Smith in 2020. And so they actually show that, well, if you go up to something which is too large, actually you get the diminishing returns. Yes, the algorithm becomes slower, but it doesn't become a square root algorithm. So the best algorithm to find collisions would be, or to find isogenies between the path, would be to use this algorithm over here, which I didn't explain, but it's basically finding reducible. You're always trying to find reducible one. You go down a dimension, you find another reducible, and you go down a dimension, you keep doing that. Yeah.
Okay, thank you.
Yeah, you're welcome.
Any more questions? Okay, if not, let's thank Bo again.